this episode, we're going to focus on a simple but powerful idea. Many attacks succeed not because attackers are geniuses, but because devices offer too many easy doors. When a laptop or server can run almost anything, install almost anything, and connect almost anywhere by default, the attack surface becomes wide, and attackers only need one small weakness to get started. Reducing attack surface means shrinking the number of ways an attacker can enter, execute code, or persist, while still allowing normal work to happen. For beginners, the phrase attack surface can sound abstract, but it becomes concrete when you think of it as all the features, settings, applications, and connections that could be misused. The three big tools we'll connect today are application control, configuration management, and isolation, and each one reduces risk in a different way. When these three are used together, they turn endpoints from flexible but fragile machines into controlled environments where fewer things can go wrong. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. A good place to begin is to understand why endpoints are such a frequent target and why their flexibility is both a strength and a weakness. Endpoints are designed to support many tasks, so they include browsers, document viewers, scripting engines, communication tools, and drivers that talk to hardware. Each of those capabilities can be helpful for a user, but each can also be abused to run unwanted code or to trick a user into doing something unsafe. Attackers prefer endpoints because they are close to humans, and humans are easier to manipulate than servers. A successful endpoint compromise can also provide a foothold to steal credentials and move deeper into an environment. Reducing the endpoint attack surface does not mean removing all functionality, because devices need to remain useful, but it does mean being intentional about what is allowed. The security goal is to make the default state safe enough that an ordinary mistake does not become a complete takeover. Application control is one of the clearest ways to reduce attack surface because it directly answers the question, what software is allowed to run? Without application control, an endpoint will often try to run whatever it is given, and that includes malicious files, unwanted installers, and scripts downloaded from the internet. Application control sets rules for execution, so only approved applications or approved publishers can run, and everything else is blocked by default or challenged. Beginners sometimes hear this and worry it will break everything, but in practice, organizations can apply it gradually, starting with high-risk areas like blocking unknown executables from user download folders. The value is that many common malware infections depend on the ability to execute something new, and if new untrusted execution is blocked, the attacker's easiest move is removed. Application control is not perfect, because attackers can try to abuse trusted programs, but it is still one of the most effective ways to cut off simple attacks. To understand application control safely, it helps to distinguish between allowing by name, allowing by publisher, and allowing by behavior. Allowing by name is fragile because attackers can rename files to look like something legitimate. Allowing by publisher relies on software being signed or associated with a known software source, which can be stronger, but it still depends on trust in that publisher and the integrity of signing. Some approaches also consider where a file came from, such as whether it was downloaded from the internet, which matters because origin is a risk signal. A common misconception is that application control is only about blocking malware, but it also reduces risk from unwanted tools that increase attacker capability, such as remote access utilities or password dumping programs. It also helps reduce accidental installation of unapproved software that may introduce vulnerabilities. For beginners, the main takeaway is that controlling execution is like controlling what tools are allowed inside a workshop, because the wrong tools can be used to damage the place even if they are not inherently evil. Configuration management is the second pillar, and it is about making device settings consistent, secure, and predictable. Many successful attacks depend on misconfigurations, such as weak local policies, unnecessary services enabled, outdated settings, or permissions that are too broad. Configuration management tries to reduce those weaknesses by defining a baseline configuration and ensuring devices stay aligned with that baseline over time. A baseline can include things like disabling unnecessary features, enforcing secure authentication settings, setting strong local security policies, and turning on protections that are off by default. Beginners often underestimate configuration because it feels like boring settings work, but configuration is where you quietly remove the conditions that make attacks easy. It also supports troubleshooting, because when devices are consistent, unusual behavior becomes easier to spot. When devices are all different, it becomes harder to tell if something is wrong or just a local oddity. One of the most important ideas in configuration management is drift, which is the gradual movement away from the desired secure baseline. Drift happens when devices are updated, when users install software, when administrators make quick fixes, or when temporary exceptions become permanent. Over time, drift can create a messy environment where some endpoints are much weaker than others, and attackers will naturally focus on the weakest ones. Configuration management reduces drift by checking devices regularly and correcting settings that slip out of compliance. This is not about being controlling for its own sake, but about maintaining a predictable defensive posture. Another important concept is that configuration management can include both hardening and usability, because a secure baseline should also support normal work. If a baseline makes the device frustrating to use, people will seek workarounds, and workarounds often create bigger security problems. Good configuration management is therefore as much about thoughtful choices as it is about enforcement. A simple way to connect configuration management to attack surface is to think about services and features that are enabled but not needed. Every enabled service is a potential target because it may contain a vulnerability or provide a pathway for attackers. If a feature is not required for the device's role, disabling it reduces the number of opportunities for exploitation. This is why baseline hardening often focuses on turning off unnecessary network services, restricting administrative shares, tightening local permissions, and limiting the ability to run scripts from risky locations. For servers, it also includes limiting exposed management interfaces and making sure only necessary ports are open. For endpoints, it might include tightening browser settings and limiting automatic execution behaviors. You do not need to memorize exact settings to understand the concept. Fewer enabled features usually means fewer places for attackers to hide and fewer entry points to abuse. The trick is to do it thoughtfully so you do not remove what is essential for the system's purpose. Isolation is the third pillar, and it is about separating risky activity from valuable assets so that compromise does not automatically spread. If you imagine an endpoint as one open room where every process can interact freely, an attacker who gets in can potentially reach many sensitive areas. Isolation tries to create safer boundaries inside the device or around certain activities. This could mean running untrusted content in a constrained environment, separating work applications from personal applications, or limiting what a process can access even if it is running. The key beginner idea is that isolation assumes some things will go wrong, so it is designed to contain the blast radius. Even if malicious code executes, isolation can limit what it can touch, what it can read, and what it can change. This is similar to having fire doors inside a building. You do not rely on never having a fire. You rely on preventing one fire from burning the entire structure. Isolation is one of the most realistic defenses because it accepts the imperfect nature of software and human behavior. Isolation also connects strongly to the idea of trust zones, where different types of data and activity are kept in separate compartments. For example, an endpoint might treat web browsing as higher risk than using a local productivity app because the web exposes the device to unknown content. A safe design tries to keep browsing activity from having direct access to sensitive data stores or privileged system settings. Another example is isolating administrative tasks from normal daily tasks so that privileged actions happen in a more controlled environment and are less exposed to everyday threats. Beginners sometimes assume isolation is only for advanced systems, but the concept appears in many everyday protections, such as separating applications, restricting permissions, and limiting what background processes can do. The security value is that attackers often rely on moving from one place to another, and isolation makes those moves harder. When isolation is used well, it turns a single compromise into a contained incident rather than a cascading failure. Now let's connect these three ideas into one mental model you can use when you encounter real-world scenarios. Application control reduces what can run, configuration management reduces what can be exploited, and isolation reduces what can be affected if something still runs or gets exploited. They map to three stages of attacker progress: execution, exploitation, and impact. Attackers want to execute something, exploit weaknesses to gain control, and then impact the environment by stealing data or spreading. If you block execution of unknown software, many attacks fail early. If you harden configurations and remove unnecessary features, exploitation becomes more difficult. If you isolate risky activity and restrict access, the impact is limited even if an attacker gets a foothold. This layered approach is important because no single control is perfect, and each one catches different failure modes. For beginners, this is a comforting message. You do not need perfect security. You need resilient security that survives imperfect conditions. A common misconception is that reducing attack surface is the same as adding more security tools, but surface reduction is often more about subtraction and discipline. Removing unneeded applications, disabling unnecessary services, and limiting powerful features can provide more protection than adding a tool that tries to detect everything. Another misconception is that surface reduction is only a one-time project, but it is really an ongoing maintenance activity because environments change. New applications are introduced, new features are enabled by updates, and new business needs arise that can pressure security controls. Surface reduction also requires communication, because users need to understand why certain actions are blocked and how to request legitimate exceptions. If the exception process is slow or unclear, people will try to bypass controls, which increases risk. A good surface reduction strategy, therefore, includes both technical enforcement and a practical way to support legitimate work. The goal is not to be restrictive for its own sake, but to make the secure path the normal path. It is also important to remember that servers and endpoints have different roles, so surface reduction should be tailored. A server that runs a specific application should ideally have only what that application needs, because extra software or services increase risk without providing value. That is why server hardening often emphasizes minimal components, strict access boundaries, and limited interactive use. Endpoints need more flexibility because users do varied tasks, but that flexibility can still be guided through application control policies and secure baselines. Isolation can be especially helpful on endpoints because so much content arrives from the outside world, like websites and attachments. Configuration management is crucial for both because drift can quietly weaken devices over time. The beginner takeaway is that the same principles apply, but the balance changes based on purpose. You reduce what is not needed, protect what must remain, and contain what cannot be fully trusted. To conclude, reducing endpoint attack surface is one of the most practical ways to improve security because it targets the conditions that make attacks easy in the first place. Application control limits what can execute, configuration management keeps devices hardened and consistent, and isolation limits damage when something risky still occurs. These ideas work best when applied as a coherent system rather than as disconnected rules, because each layer reinforces the next. If you remember that attackers depend on flexibility and excess capability, surface reduction is a direct response. You remove unnecessary options and narrow the paths attackers can take. Over time, this discipline leads to fewer infections, fewer successful exploit chains, and faster recovery when incidents occur. Most importantly, it builds a safer default environment where ordinary users can work without constantly needing to make perfect security decisions. That is what good security looks like for endpoints and servers: fewer easy doors, stronger boundaries, and a smaller blast radius when something goes wrong.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.